Welcome back, my structural analysis friends. In this video, we're going to be talking about yet another of the approximate techniques. This one involves solving for short, stiff structures that are subjected to lateral load only and is known as the portal method. So without further ado, let's get started. The portal method was a technique that was developed in 1915, or at least first introduced then, and is an approximate analysis technique for lateral loads of rectangular buildings that are very short and very stiff type structures. So normally we consider a short structure, stiff structure to be, conventional framing for a story height of, 3 to 4 feet at most. If you start getting any higher than that, some things can start to happen that don't necessarily follow what the portal method is assuming. So we've got to be very careful. But if our structure is very short, which a lot of structures are, this becomes a very valuable method and is, a very useful technique. So in this video, we'll talk about how we kind of break the structure apart, where do we, install our inflection points, and then we'll also show you, well, what do you do if you have multiple portals that are connected together? How do we move our way through that system as well? But it's very, very simple, very, very straightforward technique, but very, very powerful for getting that first estimate and that first guess. Now again, just like we've made in our other approximate methods, there are some assumptions that we have to follow. We've already talked about some of them. It has to be a short structure, 3 to 4 stories in height. Okay, it has to be fairly stiff. And then, as always, the relative stiffness of the columns have to be about the same. Okay, I can't have one really, really small column and one really, really big stiff column, because that will kind of throw off our distribution of forces. But if, most normal structures, they're all within the same order of magnitude, same size family, if you will, that's a pretty valid assumption in most cases. Okay, but again, you have to be aware of what the limitations are of the method. All right, so here's what was proposed. Okay, so a portal is basically a frame that is either pinned or fixed at the bottom and then goes up and then comes over and then comes down, back down, and it's all one basically continuous unit, that there is moment transfer through the joints, okay, that this beam is rigidly connected to the column at both ends, and that there is no hinges or anything located in the regular system. The other assumption that we make is that this method only works for horizontal loads. Okay, so there can be no vertical loads as we start to kind of look for those. Now, one of the problems that we want to be wary of is that if you have any vertical load, obviously the system breaks down. We are not worried about the self-weight of this beam. Technically that is a vertical load, but it is so small in comparison to the applied loads that we often just neglect it. We're okay with that. But again, it's an approximation. Okay, so what we're going to do is that we know from theory that if I take a point load and push on this frame is going to move laterally some amount. And normally we call that as delta, which is the story drift. Okay, and that the drift here is the same as the amount that's here, that there is no axial shortening in beam CD. And that's a pretty safe assumption. We talked about that in the last method. Kind of comparing some of the numbers when we were doing virtual work for frames. We showed that's a pretty safe assumption in most cases. When that happens, the shear moment diagram that are produced on this picture basically create inflection points at the midspan of the columns as well as the beams. And if you remember from our vertical load technique video, what we did with inflection points is we went in and we manually installed hinges at those locations. So the method that we're going to look at as we start to kind of analyze this is we're going to come in and we're going to install hinges at the mid-height of the columns and the mid-height of the beam. And that's exactly what we do. So our free body diagram then starts to look something kind of like this. So here's my A, B, C, and D, which are my original labels. This hinge is located at L/2. We're going to call that as F. Okay, the column is going to be, at a height of H/2. If H is the total height, H/2 gets me to the middle, and we're going to install a hinge there. We're going to call that E. And then on the other column, BD, we're going to install another hinge at the mid-height that we're going to call as G. And then, of course, my free body diagram has a load of P acting on it here. Okay, now, once I have that, I go from a statically indeterminate system like what we had up here that is 3 degrees indeterminate to now being able to handle this system. I now have 4 pieces. That gets me 12 equations. Okay, and then I have, 6 reactions for the hinges, and I have 6 reactions for the external support, so 12 equals 12, we're in business. This is a solvable system for static determinacy. Again, if you're having questions about the determinacy check, go back and take a look at our video on that as well. Okay, now how do I proceed to analyze this? Well, all we basically do is we're going to draw free body diagrams, okay, of our new members with the hinges in them. So the first one that I do is I draw just the top half of the structure. So I break it at the hinges that are here. So when I do that, I get a reaction at P, and then I get a horizontal reaction at E that we call EX, which I'm going to assume is to the left, and then my EY is acting down, and then my GX and my GY here, and I have everything that I need to be able to find, in this case, the axial forces in the columns. If I sum moments here, I can find this vertical, and likewise, I can then use sum of forces in the Y direction to get the horizontal. It's these, or to get the other vertical, and it's these horizontals that are the challenge. But what we can do is we can now go in on this system, and so we can see that, by summing the moments at E, I can find out that moments at C, I can find out that the moments for EY, so I sum moments, and that is the wrong location. What did I do? EY is the moment at G. Wow. So that's a G. So I'm going to sum moments here to get EY, and EY ends up being PH over 2L, and it's actually a negative value, so it's acting down on this. And then if I do sum of forces in the Y direction, well, then EY and GY have to be equal. That's what gets me GY is PH over 2L acting upward. Okay, now with those two armed for me, I can then go in and I can draw the free body diagrams for the rest of the structure. Okay, so I've got the EY. I still don't have EX. So to get EX, I'm going to go in and I'm going to look at only this piece here. Okay, and so that's what this free body diagram represents. So EY is down, EX is to the left. I have FX and FY, and so to get this EX, that's the key to this whole portal method, is to get that horizontal value. If I sum moments here, then I can sum moments at F. I can write that equation and I can find that, what do I have? I have EY times L over 2, okay, and then I have an EX times H over 2, and then I have FX times 0, FY times 0, and P times 0 all go into my equation. That's where this equation is coming from. All right, and again, I put my signs on there appropriately for this, and you can find out then that EX is equal to P over 2. So half of this load goes into that pin. And again, we've assumed that the structure is rigid and that the columns are about the same stiffness, but that's how I know how much is going into this pin. And then if this guy is P over 2, then I can come back up to this picture and do sum of forces in the X and find out that GX is also P over 2. With those two armed, now I can drop down onto the bottom column, and again, equal and opposite. So EX was to the left, EX is to the right at this location, and I know that this height is H over 2 for that side, and so then EX times H over 2 will get me the moment, and I can do free body diagram on this, and this is now statically determinate because I know EY, I know EX. Obviously, I know the height. I can find all of the reactions at the base, and so that's how we can kind of move through the system, but it's all about finding those X component values that are happening there. So pretty easy technique for what we're doing. It's all just put hinges at the mid heights, and you're good to go. Okay, all right. And so we can kind of take a look at what we have here. And then likewise, this is the algebra that goes through to find the reactions for the moments and the reactions at A. Again, we're just doing the free body diagrams on the bottom columns. I'll leave that as an exercise for you if you want to stop the video and go back and look. But at this point, this one's pretty quick. You should be able to do this by now. Okay, all right. Now, if we come in and we now look at, well, what do we do with portals that are frames that have multiple portals that are connected? Well, we kind of extend the idea. Okay, and again, we're assuming the columns are basically the same size, and we know that with one portal, it formed hinges here, here, and at the mid-height of the columns. Well, if this guy is going to be tied to this guy, then together they should form the same basic system, which means now I have inflection points at the mid-height of all beams and at all columns. Okay, and so those are our basic inflection points. Now again, this is an exterior column, this is an interior column, and this is an exterior column. Now if you remember, for one portal, what we just showed was that the horizontal force be at the bottom of the column, or really more realistically at the mid-height hinge, we found some shear value existed. This was the EX in the last picture. Okay, that we found out that from our analysis that that value was equal to P over 2. And likewise, the one at the other side was also P over 2. And so that's going to work here. Now, if you think about this, pushing here with a force P is kind of like pushing here with a force P, that there's some internal reaction that happens on this. And if they're rigid and they're tied together, that's kind of a safe assumption. So this force kind of transmits its way through the system, and I get the same effect on the second frame. So this is the frame for this side, and this is the frame for this one, and they share that column in the middle. All right, and so if this is P over 2, and this is P over 2, and that's P over 2, and that's P over 2, then the free body diagram, when I kind of combine them together, looks something like this. That the shear at the bottom is VA, that was this guy. The shear at the middle column was VB here, but it's also VB here, so I'm getting two shares of it here. And then at VC, I get a single share back on the end. Okay, and so if I do sum of forces in the X, you know, if assuming that L1 and L2, which were the spans of these things, were about the same size, which that's one of our fundamental assumptions in this, then I can do VA plus VB1 plus VB2, or let me re-speak, that these V values will all be equal values, that this was a P over 2, this is a P over 2, that's a P over 2, and that's a P over 2. All right, and then all of those are equal to some unknown V value. Okay, now if all of the columns are the same, this thing simplifies. Let's just call that as some unknown shear value V. The free body diagram on this thing now is, let's put my P back up on the top of this thing. The P is being V, 2V, and V. Okay, and so if I sum forces in the X, then I can say, well, that's 1V plus 2V plus 1V is 4V. So then each of these V's is P over 4. Okay, so now the moral of the story in this, and this is kind of a pun that when I learned it was, you know, it's kind of a Shakespeare method, that it's either 2V or not 2V. Okay, the external column in the portal, in the series of portals, gets a single share, which is what we saw up here. Okay, and this one got a single share, and then all the ones in the middle get a double share. They get 2 times V. Okay, and then all you do is just simply add them up. And so that's the basics for the method. So now you can quickly come in and say, oh, well, I'm going to do something with a bunch of columns in here. And if they're all the same, and again, the sketch is kind of sloppy, that I would get V here, 2V here, 2V here, 2V here, and V here. And if this is my P, then each of the V's, if I total that up, that's 8V is going to be equal to P. So V is P over 8. And you very quickly can build those numbers just by doing 2V or not 2V by this. And I can chain any number of these things together using that particular approach. And that's all there is to the portal method. Super, super handy for coming up with being able to break up a structure and come up with the vertical or the horizontal effects, in particular reactions for short stiff structures due to lateral loads. And then from this, once you have this all figured out, now I can come back in and I can start blowing things apart at the hinges. I can cut it at the top of the columns or cut it at the end of the beams, just like we did before. It becomes really, really easy and really, really basic to be able to start to analyze all of this. Right? So that's what we have for the method for the portal method. Super short, super easy. Gotta love it. So anyway, I hope that was clear. I know it's pretty quick. If you've got any questions with it, please leave us some feedback down below. And as always, toss us a like or subscribe to the channel, and we will see you guys next time. Have a great afternoon. Bye.